In lecture 32, we're going to be looking at an application of using trigonometry when it applies to the concept of vectors. Now, vectors are a very useful mathematical object, especially when you talk about modeling the real world. When you get into physics or other sciences where you need to talk about forces or any type of quantity that has both a magnitude, a numerical value representing its size, and also a direction in which that's applied. So things like velocity, things like forces can be represented by vectors. And since vectors have direction, it is very natural to apply some of our trigonometric concepts to that, because direction can be measured based on the angle that it makes with a certain axis, for example, the positive x-axis. So we're going to first define what vectors are. We're going to graph them, find what's called a position vector, be able to add and subtract the vectors algebraically, and then use some of our basically our understanding of geometry to do multiples of vectors and magnitudes of vectors, talk about what are called unit vectors, and then find a vector from its direction and its magnitude. And we'll look at a few more applications of vectors in upcoming lectures as well. So when we talk about a vector, what we basically mean is that idea that we have a mathematical quantity that has both a magnitude and a direction. So that's what is meant by a vector. Vectors in the plane are generally represented with arrows, and the length of the arrow can be used to then describe that magnitude of the vector, and then it's the direction that it's pointing that gives you the basically the direction of the vector, right? Since this mathematical quantity has only two properties, magnitude and direction, an arrow is very natural a tool to represent that mathematical quantity. We can also think of it in terms of the geometry related to points in the plane. If I had 2 points, namely a point P and a point Q, and I have a directed line segment, a segment that goes from P to Q, and I show that it has a direction by putting an arrow in there, okay, where the length of PQ is the distance from P to Q, and the direction is from P, your starting point, right? If I write PQ with an arrow over the top of it, that's what I mean by a directed line segment to Q. Now, if V is any vector that has that length, right, and that same direction, then we say V as a vector is the same thing as PQ, the directed line segment. Okay, note, and this is very important, the location in the plane doesn't matter. If I were to draw a vector over here and call it V, I didn't label any points, I just said there is a vector of that length and that direction. Since these two have the same length and same direction, then we say they are the same vector. If two vectors have the same direction, the same magnitude, but are located in different places in the plane, we say they are still equivalent, meaning they are the same vector, mathematically speaking. There is a special vector whose magnitude is 0 that kind of behaves a little bit differently than the rest of the vectors, because every other vector is going to have some magnitude. A vector whose magnitude is 0 is called the 0 vector. And so a 0 vector really could have a direction, but its direction doesn't change anything about the vector because it doesn't have a magnitude at all. But if you do have vectors that are non-zero, we can talk about adding vectors. And actually, you can add vectors to the 0 vector as well, as we will see. It just doesn't change the vector. We're going to add vectors. Let's start by talking about just geometrically. If you think of them as arrows, the sum of vectors can be done graphically by adding arrows head to tail. So let's say I've got this vector right here. We'll call it V. And let's say I've got this vector right here. We'll call it U. What is U plus V? I would take U, which is that vector of that length, and then I'd put V at the end of it, which is this vector of this length, right? And then the resulting vector from going from the start of the first vector to the end of the last vector, this vector right here, and I'll highlight it in yellow just to emphasize it. This vector here is u plus v. That's the sum of those two vectors. So it has some properties. Vector addition is commutative, which is the fancy mathematical word for saying it doesn't matter what order you add them in, you get the same thing either way. Right? And how can you tell that? Well, notice if I had gone u first and then, v first and then u, I still end up in the same place. So it's commutative. It's also associative, which means if I had three vectors, I can add the first two together and then add a third vector, or I can add the second two first and then add that to the first vector. It doesn't matter which order you go in, which pair you do first, you will get the same answer. Next, another property is that the zero vector is what's called the additive identity. If you take any vector v and add 0 to it, and I don't mean the number 0, I mean the vector 0, a vector that has 0 length to it. So if you're starting with v here and you add nothing to it, what do you get? Well, you get v. So the 0 vector is the additive identity. And every vector also has what's called an additive inverse. Right? There exists some vector v that I can add to v and get back to 0. Right? What vector can I add to this vector to get back to where I started? And the answer is what we'll call a negative v. And we'll talk about what negative can mean when we start talking about components of a vector. But if v is this direction, then negative v is the vector with the same magnitude but in the opposite direction. So every vector has an additive inverse. So we've talked about adding vectors together. We can also talk about multiplying vectors. We're not actually going to multiply two vectors times each other just yet. We're going to talk about what that means in later lectures, because there are actually a couple of different ways to think of what is meant by multiplication for vectors times vectors. And there has to be some specific application for you to really want to think about doing that. But if you think of multiplication in the same way that you think of multiplying real numbers, multiplying two real numbers together is a way of stretching real numbers. Like if you take the number 7 and multiply it times 3.5, you are taking the length 7 3.5 times, right? So you take and stretch something. That's really what scalar multiplication is a way of stretching vectors of a certain length. Okay, it's scaling them up. Right, so to double the number is to scale it up by a factor of 2. To half a number is to cut it down by a factor of 2. To half it, right? So quantities that have only magnitude and no direction are called scalars. So that term is our new way of thinking of just real numbers, not vectors, right? So something that has only magnitude but not direction, I'll refer to as a scalar. So let's let alpha be any real number or a scalar, and let's let v be a vector. The scalar multiple, denoted by alpha times v, is defined as follows. If alpha is a positive number, then alpha v is the vector in the same direction as v, whose length is alpha times the magnitude of v. So like 2v would be in the same direction as v, only twice as long as v. If alpha is a negative number, like say a negative 2 times v, then the only difference is we still have the same scale of the length, but we're going in the opposite direction. All right, so if we have, let's say this is v right here, then 2v would be this plus this. It would be this whole vector right here, okay? That's 2v. What's negative 2v? Well, negative 2v would be the vector going in the opposite direction, but twice as long as v, right? So it's twice the length. That's this vector right here, but in that direction. What would a 1/2 v be? Well, if this is v here, take its length in half, right? Namely this vector right there. So you can scale vectors by multiplying them by real numbers. If you have the scalar value of 1, that is called the multiplicative, fancy word for multiplication. It's the multiplicative identity. So the identity means when you do something to a number, you get the same number out of it. Well, if you take 1 times v, what do you get? The answer is obviously the same vector v, because to have a vector in the same direction as v whose length is scaled by a factor of 1, meaning multiplied by 1, it's not changed at all. It has the same length as v, the same direction as v, which means it is v. If you have a scalar multiple of -1, so if you're taking -1 times v, this is the what's called additive inverse. We defined additive inverse earlier as writing it just as -v. That's the same thing now as -1 times v, right? Because -v was the vector in the opposite direction of v, but the same length. Well, that's exactly what -1 means when you multiply a vector by -1. Opposite direction, same length, scaled by a factor of 1. Another property that comes out of introducing scalar multiples is a distributive property. If you take two real numbers, let's call them alpha and beta, and you multiply that times a vector. So you take alpha plus beta and multiply it by a vector. You are scaling the vector by a factor of alpha plus beta. You actually get the same answer as if you were to scale v by alpha first, and then scale v by beta second, and then add the two results together. You can distribute vectors over scalar addition. Okay, distributes over scalar addition, because that plus sign is between two scalars, so we're talking about just adding real numbers. On the other hand, there's also a second distributive property that also holds. That is, if you take a single scalar and multiply it times two vectors added together. So this is vector addition, because you're adding two vectors together. You get a distributive property here, alpha v plus alpha u. So it distributes, that is, scalar multiplication distributes over vector addition as well. And last of all, there is also an associative property for scalar multiplication. To take a scalar times a vector and then scale it again, you can actually just take the product of the two scalars and then scale the vector by that much, and you'll get the same answer. So these are true for any scalar multiples. All of these properties hold. As an exercise in understanding the graphical nature of our scalar multiplication and our vector addition and subtraction, let us think of these three vectors in terms of their direction and magnitude. The easiest way to just keep track of the size of these vectors is to realize that u goes 2 over and 3 up, v goes 2 over and 2 down, and w goes 3 over and 1 up. That'll help us as we add through these. Let's talk about part A. Okay, v minus w. So you start with v. Let's go, let's start right here. V is this direction. There is v. And then a minus w. Now w would be over 3 and up 2. So minus W would be left 3 and down 1. So this right here is W, but negative. All right, so it is, sorry about that, this vector right here, which I'll go ahead and highlight, this vector here, right, is the answer to part A. The vector that starts here goes down 3 and over to the left 1. There is my answer to part A. All right, what about part B? Let's talk about part B. So we got to do 2v. So let's start, let's say here. 2v would be, here's 1v. 2v would go down this way. So that's 2v right here, this vector all the way to right here, because it's the same direction as v, only twice as long. And then 3w means go over 3 and up 1, over 3 and up 1, over 3 and up 1. There's 3w. So the answer to part B is this vector right here. This is the vector that goes over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and down 1, because I ended up right there. So I'll highlight it just so you can see which vector I'm talking about. This one right here is the answer to part B. And then C, we're going to do 2v and then minus w and plus u. So let's start here. 2v, there's 1 and 2. Hopefully we don't leave here. Yep, there's 2v. Minus w is left 3 and down 1, so minus w here. And then plus u, u is up 3 and over 2. 1, 2, 3, over 2. There's u. So this vector that goes over 2, sorry, over 3 and down 2, that vector right there is the answer to C, which I will also highlight for your reference. This vector right here is the answer to part C. There are better ways for us to mathematically represent vectors than just to use arrows. One of the ways to do that is to break it down into the components. Now, first of all, let's talk about a couple of important concepts and then describe what are called position vectors. Note that a vector v is, we can denote the magnitude of a vector v by using the absolute value symbol. It means that right there is the length of the vector v, and I write a bar over the top to make sure we understand that that v variable represents a vector. And for any vector u such that the magnitude of u is exactly 1, we call that a unit vector. Vectors of length 1 are called unit vectors. We then give a special name or a special symbol, I as a vector, not I the complex number. This is actually a vector I. We call that the unit vector whose direction is along the x-axis. So a vector that goes this way, whose length is 1, is called I. And I put I with a line over the top of it. And then j is the vector whose direction is along the y-axis. I should probably be, I'm sorry, let's fix a couple things here. Positive x-axis and positive y-axis. So the vector going straight up, whose length is 1, is called j. Now if v is a vector with an initial point at the origin and its endpoint, its terminal point, is some point in the plane, then we can denote the vector v by writing it in terms of its components. A times I plus B times J. And the scalars A and B are called the components. of that vector. So think of it this way. If you've got a coordinate system, and here's your origin, and here is your point, and the coordinates of that point are A, B, meaning that this distance here is A, and this distance here is B. If I had a unit vector, and I stretched it from being one length to A, that vector that goes along here, and I'll draw this in red, this vector along here is A times I, because it's the unit vector in the positive x direction stretched to be a length of A. And this vector right here would be Bj, because you start with J, which is length 1, and stretch it to a length of B. And now if you add those two up, the vector you end up with is vector V, given by this notation right here. So we can write vectors in terms of their x and y components. A is their x component, B is their y component. Now alternatively, if the vector is not starting at the origin, say it starts over here at a point x1, y1, and ends over here at a point x2, y2, and we want to look at the vector that goes from this point P to this point Q, right? Then the vector that is represented by PQ, right, we've got to break it down into its components. So how far does it go in the x direction, and how far does it go in the y direction? This distance here would be x2 minus x1. So the x component would be x2 minus x1 times I, and then the y component, this length vertically here, would be y2 minus y1. So we would have plus y2 minus y1 times j. Now there's a couple of different ways we can write vectors going forward. We can write it in the notation we've been using, AI plus bj. We can also write it using this angle bracket notation, just so that you can tell the difference between it and the point notation, the ordered pair. Let's just look at a couple of examples just to make sure we understand these concepts. Let's say V is a vector that goes from point 1 to point 2. We want to write down its position vector. By position vector, I mean this notation right here. So vector V would be x2 minus x1 I plus y2 minus y1 j. So x2 and y2 is the ending point, and x1, y1 is the starting point. So you end up with 3 minus a minus 2, which was 3 plus 2, plus 4 minus a 1 times j, which gives me 5i plus 3j. And that's your position vector, which we could also write as 5, 3 inside these angle brackets. It just means the same thing. It's alternative notation. So note, let's consider two vectors that are both written in position form. These are position vectors. So we have, they each have an x and a y component. The x component of V is A1. The y component of V is B1. The x component of W is A2. And the y component of W is B2. To add two vectors together, previously all we did was draw the arrows and add them head to tail. But we can now do it mathematically. To add these two vectors together is to add their components. So if V goes A1 in the x direction and W goes A2 in the x direction, then the sum of those two vectors would be A1 plus A2 in the x direction, and then B1 plus B2 in the y direction. If you were to subtract them, A1 minus A2 and B1 minus B2. Times j. If you want to multiply a vector by a constant, then you just multiply each component by that constant. Like that. And if you want to find the magnitude, and I need to correct something, the notation that's used in your book is an alternative to what I wrote above. So let's go ahead and flip back to the previous page when I told you that the magnitude of V was absolute value of V. In your homework and in your book, they actually use the double bar notation instead of a single bar notation. So that's what you will see when they ask you for the length of the vector V. So how do I find the length of a vector V? Well, this is actually just from Pythagorean theorem. If I know this length right here is A1, and this length right here, which is this height here, is B1, then how long is this side? And you can use the Pythagorean theorem to get the answer. Namely, it would be the square root of A1 squared plus B1 squared, right? Because A1 squared plus B1 squared would be that hypotenuse squared, and just square root both sides, and you get that right there. So let's do this with a few examples. Let's add two vectors together. So I've got 2i plus 3j and 3i minus 4j. I want to add them together. All right, so this is like 2i plus 3j added to 3i minus 4j. And even though we got formulas up here above, you can see really all this is collecting like terms. Put the i's together and the j's together. You get 5i minus j, right? Because 2 plus 3 is 5, and 3 minus 4 is a minus 1, so you have a minus 1j. Okay? You could also think of this in terms of their angle bracket notation, right? Because V is 2 comma 3, right? 2i plus 3j is 2 comma 3, and 3i minus 4j is 3 comma negative 4. And to add these two vectors together, just add their components. Add the 2 plus the 3, you get 5. Add the 3 and the negative 4 together, you get negative 1. And notice how these two answers are the same. If I take 2 times a 2i plus 3j minus a 3 times a 3i minus 4j, notice I can just use my algebra rules to get this by distributing, because that's all multiplying by alpha does, is distribute the alpha to both terms. So you get 4i plus 6j minus 9i plus 12j, and collect like terms. 4i minus 9i is negative 5i, and 6j plus 12j is plus 18j. So it goes negative 5 in the x direction and 18 in the y direction. And I could alternatively use the angle bracket notation, but I'm going to go ahead and just say this approach is my preferred approach. Now, to find the magnitude of the vector v, I would take the square root of the first component, which is 2, and square it, plus the second component, which is 3, and square it. You get the square root of 4 plus 9, which is the square root of 13. That would be the length of this vector v. For any non-zero vector, we can come up with a unit vector that goes in the same direction as the vector v. So, for example, if we would like to have a vector v that looks like this, we know its length is denoted by the double bar notation of v, right? So how do we get a vector that goes in the same direction whose length is only 1? What we would do is we would take the long vector and divide by and scale it so that its length is now 1. So basically you want to take the length of it and divide it by itself. That is, you've got this long vector here, its length is absolute value of v. or the magnitude of v, if you divide this vector by this number, you will end up with a vector whose length is now 1, because dividing by the scale will shrink that vector by whatever factor. If you remember, if you divide by 2, you cut it in half. So if your original vector was 2 and you divided its vector by 2, you would end up with one that was a length of 1, because you are dividing the length by whatever the scale is. So if I take v and divide it by the magnitude. Now remember, magnitude is just a number. This is a vector. So really this is more like taking 1 over the magnitude of v times the vector v, right? This is a scalar that you're multiplying times the vector v. The result now is you will have a vector that is a length 1, but goes in the same direction as v. That turns out to be a very useful tool when we start using vectors to model things in the real world. So just to see how it works, if you took the vector 3, -4, we know how to find its magnitude, right? The magnitude of v is the square root of 3 squared plus -4 squared. That is the square root of 9 plus 16, or the square root of 25, which is 5. So the unit vector in the direction of v would be the vector v over its magnitude. Looks like this. It's 3, -4 times 1 over the magnitude. That's this value right here. So you get 3/5 -4/5. You just take that 1/5 times each thing. This vector right here, 3/5, -4/5, has a length 1, and it goes in the same direction as the vector 3, -4. Another operation we can do is we can find a vector when we are given its direction and its magnitude. So suppose we know the two properties of a vector. We know how long it is, and we know what direction that it goes. Meaning maybe we know the angle of the vector when it's starting at the origin. That's direction. Up to this point, we've known things like the x component and the y component and work with the vectors there. So let's say we're given just its length and its and its direction. Can we find the components of that vector? So suppose we are given a vector with magnitude v, a double bar v, and the direction angle, which I will call alpha, where alpha is between 0 and 360 degrees. And what I again mean by a direction is if you put your vector where its starting point's at the origin and it has a certain direction, say that's v, we know its length is the magnitude of v, and the direction angle is what is its standard angle in standard position. So that right there I call alpha. That's its direction angle. Then we can write this vector in terms of where this point is right here. And actually there's enough information now for us to figure that out trigonometrically, because if you put this on the outside of a circle whose radius is the magnitude of v, then we know the coordinates of that point are the radius of the circle times cosine alpha for the x component, and the radius of the circle times the sine of alpha for the y component. That's something we've already covered and used whenever we introduced polar coordinates. So now this is connected to polar coordinates as well. That's why polar coordinates was the very first topic of of this lecture section. So now, based on that, we would say vector v is the magnitude of v times cosine of alpha in the x direction plus the magnitude of v times sine of alpha in the y direction. And it's the direction angle A is that angle that vector v makes with that positive axis. That's where we got where this was drawn right here. So let's use that to answer a couple of questions. So if I know the value of the magnitude is 8 and alpha is 45, then vector v is clearly 8 cosine of 45 times I plus 8 times sine of 45 times j, which is 8 times the square root of 2 over 2, I, plus 8 times the square root of 2 over 2, j, or 4 square roots of 2, I, plus 4 square roots of 2, j, just like that, which we could also write as 4 square roots of 2, comma 4 square roots of 2 inside the angle brackets. Another one just like it, if I want to find the vector in its component form, when I know its length is 15, it's 15 cosine of 330 times I plus 15 times sine of 330 times j. The cosine of 330 degrees would be the square root of 3 over 2 I, and then the sine of 330 degrees would be a negative 1/2. So that gives me 15 square roots of 3 over 2 times I minus 15 over 2 times j, or in angle bracket form, just like that.